Dad! Oh my god. Oh, there we go. Welcome. Welcome to this stream. Like I said yesterday, I'm gonna stream. Like I said yesterday, I'm gonna stream. Today. So this is no good, yeah. Today we are gonna read about NMR. I don't know why it says mass. There we go. NMR, baby. NMR. So yeah, hopefully everything will be alright, and yeah. Hold on. Oops. Like this, yeah. Much better. And I also got my sweet, sweet oatmeal that I also have to eat. Oatmeal. I eat these like every morning. It's such a good thing. Mhm. 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 Oatmeal is always good. All right, testing if um my alerts is working. Yeah, everything works. Cool. Now let's understand this piece of mm, 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 mm. This is just the theory of NMR. Oh, there's something here. Okay, those are the different ppm levels of the NMR. Hybridization and resonance. Typical ranges for protons with variable chemical shift. Okay, so if it's under 15, it's either this. If it's at 7, it's phenol. Alcohols are at 0.5 to 5.0. Okay. One, two, three. This is a duplet. That means, yeah, this is this one. 1, 2, 3, 4. Triplet. Yeah, so this is the neighbor. Yeah, okay. And what the hell is the iodine? It's just there. Definitely, you have to remember a lot of patterns. That's basically with spectroscopy. Okay, 8, 1, 2, singlet, and then I have 6. That means there's 2 of, yeah. Yeah, exactly. This is, yeah. 1, 2, 3, 4, 5. Sep, 6. Yeah, so, yeah. Common examples of observed splitting pattern in compounds. Okay, so there's 2, 3. 1, 2, 3. That's 1H. Multiplex skewing. ×60 megahertz. The acetylenic hydrogen will be absent if the triple bond is in the middle of the chain. Hmm. Deuterium exchange. Eight spectrum of 2 methyl propanol. How do I know there's an alcohol? Okay, so oh shit, okay, there's a peak. One is ever. Then it has a large peak. Mm-hmm. Mm. Yo, what's up, Tech? What's up, man? Welcome to the stream. Sorry for being so quiet. I'm just like concentrating for now, and then I'll explain. Welcome to the stream, man. Hmm. Hmm. Oh, it's getting a bit cold. Okay, everybody, let's read about array functions. All right. The wave function. Um, Postulate 1, the wave function. Quantum mechanics acknowledges the wave-particle duality of matter by supposing that rather than traveling along a different path, a particle is distributed through space like a wave. The mathematical representation of this wave is called the wave function, psi. A principal tenet of quantum mechanics is that wave function contains information about all the properties of the system that are open to experimental determination. This discussion is summarized by the first postulate of quantum mechanics. Postulate 1. The state of the system is described as fully as possible by this wave function psi r1, r2 to t, where r1 and r2 are the location of the particle and t is the time. So the wave function psi r1, r2, t is called the time-dependent wave function. If the wave function does not depend on time, it's written If the wave function does not depend on time, it is written psi r1, r2 are called the time-independent wave function. In most of the introductory topics, we shall be concerned with systems that consist of single particles and do not vary with time, so the wave function is denoted as psi r. Where r is the location of the particle. In simplest application, the system is one-dimensional, so the wave function is simply a function of x, and we write it psi x. For simplicity, we often denote the wave function as the plain letter psi. Okay. I can't even see the thing. That should be much better. I'm just enjoying eating my oatmeal right now. I had a lecture from 8 a.m. to 2 p.m. So I might sound a bit tired. I'm sorry about that, but yeah. And I have laboratory tomorrow with my group. Anyway, let's get started with this stream now. Okay. Let's go! Okay. There are two approaches to the formal introduction of quantum mechanics. One is to see the theory gradually emerging from the start of Planck, Einstein, Heisenberg, Schrödinger, and Dirac. I don't know who Dirac is, but he sounds cool. In which experiment and intuition together determine the form of the theory. The other approach is to stand at the point in time at which the theory has already been well the wave theory of light, in which the square of the amplitude of an electromagnetic wave in a region is interpreted as its intensity, and therefore in quantum terms a measure of the probability of finding a photon present in the region. Probabilities and probabilities are densities. The Born interpretation of the wave function focus on the square of the wave function is psi is real, or the square modulus psi squared in it's complex, where psi asterisk is the complex conjugate of the wave function. Okay. Postulate 2. For a system described by wave function psi r, the probability of finding the particle in the volume element d something Greek at r is proportional to psi r2 squared. Thus, because psi squared must be multiplied by the volume to obtain the probability, just like mass density must be multiplied by the volume of the body to get the body mass. It is called a probability density. In line with this usage, the wave function psi itself is called probability amplitude. The prime of this postulate number will be discarded when it's generalized to more than one particle at the end of this section. The wave function might be negative in some regions or even complex. However, the Born interpretation does away with any worry about significance of such values because psi squared is real and never negative. There is no direct significance in negative or complex value of the wave function. Only the square modulus of positive positive quantity is directly physically significant, and both negative and positive regions of the wave function may correspond to a higher probability of finding a particle in a region. However, later we shall see that the presence of a positive and negative regions can't even read, of a wave function is a great indirect significance, because, like waves in general, it gives rise to the probability of constructive and destructive interference between different wave functions. When we come to deal with atoms and molecules, we need to be aware of the interpretation of the wave function for a system. Don't be alarmed at the thought of having to manipulate complex wave function. They can be as simple as sinus x or e minus x. Wave functions might be complex in the technical sense of depending on I equals -1/2, see the chemist's toolkit, but even then are often simple in colloquial sense as in e I k x. Postulate 2. The Born interpretation. The interpretation of the wave function is based on a suggestion by Max Born in 1926. He made use of an analogy with more than one particle, such as 2 electron helium atoms and 16 electron O2 molecule. In this case, psi r and 2 is used to calculate the overall probability of finding each particle in its own specific volume element. The generalization of postulate 2 is then postulate 2. For a system described by a wave function, psi r1 and r2, the probability of finding particle 1 in the volume determined element d something t theta, I think, at r1, particle 2 in the volume element of d theta 2 and r2, etc., is proportional to the modulus of the psi. Normalization. Postulate 2 refers to a probability between probability and psi 2 modulus. To determine the actual value of the probability, we write psi slash or what? A colon? No, that's a slash, I think. We write psi I don't know. What do you call that? That's yeah, okay. Psi mark. I'm gonna call it mark equals n psi, where n is a real constant selected, so that psi mark modulus is equal to the probability that the particle is in the volume element d theta. To determine this constant, we note that the total probability of finding the particle anywhere in the space must be 1. It must be somewhere. If the system is one-dimensional, the total probability of finding the particle is the sum integral of all the infinitesimal contributions. So psi mark modulus, and we write the integral of, okay, so minus infinity to infinity, and then the psi. A wave function then satisfies condition phi 1 is said to be strictly normalized to 1. In terms of the original wave function, this equation becomes n2. Okay, so this follows the normalization constant n is given by, okay. Almost all wave functions go to 0 at sufficiently great distances, so there are rarely any difficulty with the evaluation of the integral in equation 5.2. Wave function of which the integral exists in the sense of having a finite value are said to be square integrable. From now, unless we state otherwise, we always use wave functions that have been normalized to 1. That is, from now on, we assume that psi already includes a factor which ensures in one dimension. So the normalization condition in one dimension is this, and in 3, that's this one. So it's in one dimension is dx, and if three dx, dy, and dz. In general, the normalization condition may be written as, okay, where dt stands for the volume element in the appropriate number of dimension, and the limit of integration are not written explicitly. In all such integrals, the integration is over all the space accessible to the particle. The wave function must satisfy stringent conditions for it to be acceptable. A, unacceptable because it's not continuous. B, unacceptable because its slope is discontinuous. C, unacceptable because it is not single valued. D, unacceptable because it is infinite over a finite region. Okay. Oh my god, bro. My hair. I hate really my hair, bro. Yeah, whatever, bro. Whatever, bro. C, constraint on the wave function. The Born interpretation puts severe restriction on the acceptability of the wave function. The psi must not be infinite over an infinite region, psi must be single valued, psi must be continuous, and the slope of the wave function, that is d psi x, must be continuous. These restrictions are summarized in figure blah blah blah. If psi or if wave function were infinite over a finite region, it would not be square integrable, and the Born interpretation will fail. Note that the emphasis on the finite region and an infinitely sharp spike is acceptable provided it has zero width. The constraint that the wave function must be single valued, that is, have a single value at each point of space, is also a consequence of the Born interpretation, because it will be observed to have more than one probability that a particle is at the same point. The remaining two constraints, the continuity of the wave function and its first derivative, ensure that it can be calculated from the second order differential equation. The Schrödinger equation, which we introduced shortly, that equation depends on second derivatives of psi, which is d2 psi dx2, which exists only in psi and d psi x are continuous. Once we have obtained the normalized wave function, we can then proceed to determine the probability of finding the system in a given finite region of space by summing that is integrating the probability density over a region of space of interest. For example, for a one-dimensional real wave function, the probability of finding the particle between x1 and x2 is given by, okay, this one. Oh my god. The wave function contains information about all the properties of the system that are open to experimental determination. The Born interpretation gives the probability of finding the particle in a region of space. Wave function must be single value, continuous, not infinite over a finite region of space, and have continuous slopes. extracting information from the wave function. Postulate 3, the quantum mechanical operators. In 1926, the Austrian physicist Erwin Schrödinger proposed a special second-order differential equation for finding the wave function of any system. This time-independent Schrödinger equation is for the particle of mass m moving in a one-dimension with energy E is... Holy shit, what the hell am I looking at? One-dimension time-dependent Schrödinger equation, okay. That's one dimension. It looks... oh my god, okay. Where V is the potential energy of the particle and H slash is the Planck constant divided by 2 pi, which is read H cross or H bar, is a convenient modification of Planck's constant. Extensions of Schrödinger equation is more than one dimension and its time dependent form shown in table 6. Okay, we could regard equation 6.1 itself as a postulate, but it turns out to be far more fruitful to interpret it in a special way and in regard to as consequence of deeper, more general postulates. Equation 6.1 and its multi-dimensional counterpart in table 6.1 may all be written in a yeah, okay. Succinct form. Okay, so we have H triangle psi and equals E psi. Holy shit! That's 2 dimension. Oh my god, okay. General case, okay. 1 dimension, 2 dimension, 3 dimension. Coordinates. What in the hell, man? Time dependent. That's time independent. Oh, what the, okay. When 1 dimension, I'm reading. Yeah. We're in 1 dimension, this Hamilton operator. For a reason that will shortly become clear, we have noted that the potential energy of the particle depends on the position x, and have included the multiplication sign explicitly. The quantity h is an operator, or something that carries out a mathematical operation of the function psi. In this case, the operation is to take the second derivative of psi, and after multiplication by this whatever minus h bar 2, okay, to add the result to the outcome of multiplying psi by the value of v at the position x. The operator h, as well as all the other operators encountered in the quantum mechanics, is linear in the sense that, okay, so that was the general term, right? Okay. For any function psi, wave function 1 and wave function 2, and any constant c, the operator h plays a special role in quantum mechanics. It's called the Hamiltonian operator. After the 19th century mathematician William Hamilton, who developed a form of classical mechanics that it subsequently turned out is well suited to the formulation of quantum mechanics. We can infer from the form of equation 6.2a that the Hamiltonian operator is the operator corresponding to the total energy of the system, the sum of kinetic and potential energies. It then follows that the first term in equation 6.2b, the term proportional to the second derivative, must be the operator from the kinetic energy equation 6.2a is highly suggestive of a more general formulation. First, it suggests that there might be observables or measurable properties of a system that can be represented by other operators that are the structure energy operator Hamilton psi equals value of energy and then psi. It's a special case of more general form operator for observable omega psi equals value of observable times psi. From now on, we represent the operator corresponding to the observable uppercase omega by omega triangle and the value of the observable by lowercase omega. And write the last equation as okay. Our immediate problem is to discover how to formulate the once again, the equation 6.2 gives us a clue in classical mechanics. The total energy of particle in one dimension can be expressed in the terms of linear momentum P as okay, this one. Oops. Comparison of this expression with equation 6.2b strongly suggests that the operator from position x is just a multiplication by position xx. Because the positional energy Vx is represented by a multiplicative operation Vxx. Further comparison with equation 6.2b suggests the operator for kinetic energy P2 divided by 2m can be identified with minus h bar 2 divided by 2m d2 dx into. Now we bring these points together by formulating a postulate that summarize them. Postulate 3. For each observable property ohm of a system, there is a corresponding operator omega uppercase omega built from these following position and linear momentum operators. So we have a position operator and we have a linear momentum operator. So then we have two operators working with. The multiplication sign for multiplicative operators is not normally written, and from now on we shall omit it. What the hell is omit? However, it must always be remembered that x is the operation that multiplies any function on this right. When we are discussing one-dimensional system, we discard the index x on p for three-dimensional system. We use subscript x, y, and z to denote the competence of vector p along each direction with the corresponding operators defined analogously. Okay, I'm not gonna read that word. With postulate 3 established, we can immediately write down the operator for the kinetic energy Ek for a particle in one dimension, because Ek equals p squared minus 2m. It follows the kinetic energy operator is okay, and therefore because in mathematics, the second derivative of a function is a measure of a curvature. A large second derivative indicates a sharply curved function. It follows that a sharply curved wave function is associated with a high kinetic energy, and one with a low curvature is associated with a low kinetic energy. This interpretation is consistent with the de Broglie relation, which predicts a short wavelength, a sharply curved wave function. Okay. So we have a low curve and we have a high. So when it's high kinetic energy, the curve gets higher, and when it's low, it's lower. Okay. Which predicts a short wavelength A sharply curved when the function that occurs on both sides of the equation is called what? When the function that occurs on both sides of the equation is called the eigenfunction of the operator. Each eigenfunction corresponds to a specific eigenvalue. In terms of this new language, by referring to equation 6a, it follows that the other way of saying solve the Schrödinger equation is to say find the eigenvalues and the corresponding eigenfunction of the Hamiltonian operator of the system. The wave function are the eigenfunctions of the Hamiltonian operator, and the corresponding eigenvalues are the allowed energies. Eigenfunctions and eigenvalues as operators play a crucial role in quantum mechanics, and we counted them throughout the text. Oh, okay, shit. Oh shit, my bad. I have to read it like this. Postulate what? 4 eigenvalues and eigenfunctions. At this point, the presentation of postulate of quantum mechanics, we know how to construct operators for observable. The wave function, a solution of the Schrödinger equation. The observable ohm is influenced by the value of lowercase o omega in the operation. Okay, where this omega hat or something is the corresponding operator. We need to develop this last point. First, we know the equation 6.3 has the form operator function. Okay, we have the operator and then the function, which give us the eigenvalue and the eigenfunction, which gives us the same function. An equation of this form is called the eigenvalue equation. The numerical factor is called the eigenvalue of operator, and yeah, that's for the. The far-reaching consequence, the result, the interpretation of equation 6.3 in the Schrödinger equation and the eigenvalue equation. First, we need to know that the allowed value of a observable ohm, such as energy E, is the eigenvalue in the eigenvalue equation. Therefore, once we have found all permitted eigenvalues of an operator, we shall know the permitted values of the observable. Each eigenfunction corresponds to a particular eigenvalue. Specifically, each wave function corresponds to a particular energy. And we already seen that there's a real restriction on the acceptability of wave functions. We can anticipate, therefore, that because only certain wave functions are acceptable, only certain eigenvalues are allowed. In other words, in general, an observable is quantized. We summarize the discussion so far in the language introduced in the section with the following postulate. Postulate 4, right? Yeah, 4. If the system is described by a wave function psi that is an eigenfunction of omega hat, such as omega hat times psi equals lowercase omega and psi, then the outcome of the measurement ohm or omega will be eigenvalue lowercase omega. Okay. Because the value of an observable is a real quantity, real that is in mathematical sense of not involving the imaginary number I. Postulate 4 implies that the eigenvalues of any operator that correspond to an observable must be themselves be real. Be real. Isn't that like an app? The reality of eigenvalues is guaranteed if the operator has a special property of hermeticity. Named for the 19th century French mathematician Charles Hermite, a Hermitian operator is one for which the following equality is true. Okay, where f and g are any two wave functions, it is easy to confirm that the position operator xx is Hermitian. 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 What the hell? Okay, because we are free to change the order of the factors in the integrand. The demonstration that a linear momentum operator is the Hermitian is more involved because we cannot just alter the order of function. We differentiate, but it is Hermitian, as we show in the following justification. Oh shit, okay. The wave function is the solution of the Schrödinger equation. For each observable property omega, uppercase omega, of a system, there is a corresponding operator, omega hat, built from the position and linear momentum operators. If the system is described by a wave function psi that is an eigenfunction of omega hat, such as omega hat psi equals lowercase omega psi, then the outcome of the measurement omega will be eigenvalue, and the eigenvalues of an Hermitian operators are real. Okay. You know that feeling when your feet is sleeping? That's me right now. Like I can, Topic 6, postulate 4 tells us that if the wave function is an eigenvalue of the operator corresponding to an observable, then the easy identify the value of that observable, we just pick out the corresponding eigenvalue. Suppose, though, that the wave function is not an eigenfunction of the operator corresponding to the property of interest. What can we then say? For instance, suppose the wave function is cos x kx. This wave function is an eigenfunction of the kinetic energy operator, which eigenvalue k2 h2. So we know that the measurement of the kinetic energy will certainly give that value. However, cosinus kx is not an eigenfunction of the linear momentum operator because the where was I? Cosinus kx is not an eigenfunction of the linear momentum operator because the cos kx divided by dx equals minus k sinus kx. Okay, now they're just making up equations. And so in this case, we cannot use postulate 4 to predict the outcome of the measurement of the linear momentum. In this topic, okay, nobody cares. Wave functions, linear combinations. The clue we need in order to make progress in the case of the wave function cos x kx is to know that we can use Euler's formula. Okay. Each exponential function is the eigenfunction of the linear momentum operator, with eigenvalue plus kh and minus kh respectively. We say that the actual wave function is a linear combination of two contributing wave functions, namely eikx and e minus ikx. In general, a linear combination of two functions f and g is c1 and c1f plus c2g, where c1 and c2 are numerical coefficient. So a linear combination is more general term than sum, for which c1 equals c2 equals 1. Other ways to express the fact that the wave function is a linear combination of individual wave functions is to say that the state is a superposition of individual states. At this point, we recognize that the wave function cos kx can be written symbolically as this. Interpretation of the composite wave function is that the momentum of the particle is repeatedly measured in a long series of observations. Then its magnitude will be found in the kh in all the measurement, because that is the value for each of the eigenfunctions. However, because the two eigenfunctions occur equally in the wave function, the same numerical coefficient occurs in the linear combination. Half the measurement is will show that the particle is moving to the right, and half the measurement it will be showing that it's moving to the left. According to quantum mechanics, we cannot predict in which direction the particle will in fact be found to be traveling. All we can say is that in a long series of observation, the particle is described by this wave function. Then there are equal probabilities of finding the particle traveling to the right and to the left. Furthermore, since half the measurement yield, we expect the average value of a large number of measurements to be 0. This discussion motivated the following generalization to the case when the system is known to be a linear combination of many different eigenfunctions of the operator corresponding to the observable of interest, and is written as where the ck are numerical and possibly complex coefficient, and the psi k or wave function k correspond to the different eigenvalues of the operator, which omega hat and wave function k equals. Then postulate 5. When the value of an observable omega is measured for a system that is described by a linear combination of eigenfunctions of omega hat, which coefficient ck, each measurement gives one of the eigenvalues omega k or lowercase omega k of omega hat, which are probability proportional to ck2. If the system is described by a wave function that is normalized, then the probability of obtaining the eigenvalue lowercase omega k is equal to the modulus of ck. Mean values as expectation values, because in general a series of measurement of a property gives a number of different outcomes. It is often important to know that the average value of these outcomes, that mean that is average value from measurement of the observable omega, is equal to expectation value of the operator, denoted and defined as, okay. This definition applies whether or not the wave function is written as a linear combination of the eigenfunction. For a normalized wave function, the denominator in equation 7.2a is 1, and this expression simplifies to, all right, if wave function if psi happens to be an eigenfunction of omega hat, then by postulate 4, every measurement of the observable will yield a single eigenvalue, and therefore the average value is also lowercase omega. In this case, the expectation value of omega hat is simply, if psi is not an eigenfunction of the observable of interest, each measurement of the property gives a different outcome. To investigate the relationship between the outcome of a measurement and the expectation value, we need to develop another feature of eigenfunctions. That we shall do in the following topics, and also provide a foundation for the justification of postulate 5. As we shall see, functions that are both orthogonal and normalized are said to be orthonormal. Okay, where delta ij, which is called the Kronecker, Kronecker delta, is 1 is 1 when I equals j, and 0 when I doesn't equals j. Okay. The orthogonality of eigenfunctions. A very special feature of Hermitian operators is, as we show in the justification below, that the eigenfunction corresponding to different eigenvalues of the same Hermitian operators are orthogonal. To say that two different functions psi I and psi j are orthogonal means that the integral all over space of their product is 0. So it equals 0 everything. For example, the Hamiltonian operator is Hermitian. is correspond to observable the energy. Therefore, if wave function I correspond to one energy and wave function J correspond to a different energy, then we know at once that the two functions are orthogonal and the integral of the product is 0. Being able to set integrals to 0 in this way greatly simplifies the calculations. Uh, Normalized wave function is the sum of two eigenfunctions. The general case can easily be developed from equations 7.2b. The first two integrals on the right are both equal to 1 because the eigenfunctions are individually normalized. Because the wave function 1 and wave function 2 correspond to different eigenvalues of a Hermitian operator. They're orthogonal. So the third and fourth integrals on the right are 0. We can conclude that, okay, in the general case, where psi x is an eigenfunction of omega with an eigenvalue lowercase omega k, the expectation value is given. Linear combination. Okay. Equation 7.4 shows that the expectation value is weighted to average of the eigenvalues omega hat, which the weighting equal to the square modulus of the expansion coefficient ck. This is the basis of postulate 5, for it strongly suggests that the measurement of the property omega gives a series of values lowercase omega k with an occurrence that determined by the value of ck. All right. Checklist of frick. A state that is a superposition of individual states is described by a wave function that is linear combination of the corresponding individual wave functions. When the value of observable omega is measured for a system that is described by a normalized linear combination of eigenfunction of omega hat, which coefficient ck with each measurement gives one of the eigenvalues lowercase omega k of omega hat, which a probability equals to ck modulus of 2. The expectation value of the operator omega hat denoted, okay, is equal to the mean value of a series of measurements. Eigenfunctions corresponding to different eigenvalues of the same Hermitian operator are orthogonal. The 5 postulates of quantum mechanics are collected in the summarized form. Here the conventions. The state of the number 1. The state of the system is described as fully as possible by a wave function psi r1, r2 to t. Number 2, postulate 2. For a system described by a normalized wave function, the probability of finding a particle 1 in a volume element dt1 and r1 in particle 2 in the volume element d2 t theta 2 at r2 etc. equals to modulus of the wave function. Postulate 3. For each observable property omega of a system, there is a corresponding Hamilton operator. Omega hat built from x hat equals xx and p hat x equals h bar divided by I dx d and dx. That was the momentum. The x was momentum operator and the p was the linear operator. If the system is described by wave function psi, that's positive 4. Psi, then the eigenfunction of omega hat with the eigenvalue lowercase omega, then the outcome of the measurement of the observable property omega will be omega lowercase omega. If the system is described by a normalized wave function, this is postulate 5, psi with that linear combination of eigenfunction of omega hat, then the outcome of the determination of the observable omega will be one of the eigenvalues lowercase omega k of omega hat with probability ck modulus 2. The mean value of measurement is equal to the expectation value. All right, cool. Okay. The uncertainty principle. Complementarity. What is these words like? What the hell? What? Some of the profound differences between quantum mechanics and classical mechanics can be appreciated by considering a particle traveling in one dimension towards positive x with a linear momentum plus k h bar. According to classical mechanics, we can specify the trajectory of a particle is its location and momentum at all times. According to quantum mechanics, the state of a particle is described by wave function neikx, where n is the real normalization factor. Such a wave function corresponds to a well-defined linear momentum. Its eigenvalue is kh bar. But where is the particle located? To answer this latter question, we use postulate 2. Topic 5. To calculate the probability density. Alright, cool. This probability density is independent of x. So wherever we look at the x-axis, there is an equal probability of finding the particle. In other words, if the wave function of the I need to sneeze so bad. Of the sorry. Okay, of the particle is given by neikx, then we cannot predict where we will find the particle. The extraordinary conclusion is that if we know the line momentum precisely, then we can say nothing about the position. This complementary of certain pairs of observable in this case, line of momentum and position pervades the whole of quantum mechanics. How do we recognize? Okay. The Heisenberg uncertainty principle. We have seen that if we know the line momentum of a particle precisely, then we can say nothing about its location. But what of opposite problem? Can we know the line momentum of a particle if we know the position precisely? That we cannot can be deduced as follows. If we know that the particle is a definite location, its wave function must be large there at zero everything else. Such a wave function can be created by superimposing a large number of harmonic sine and cosine function or equivalently a number of E1kx functions. In other words, we can create a sharply localized wave function called a wave packet by forming a linear combination of wave functions that correspond to many different linear momenta. The superposition of a few harmonic functions gives a wave function that spreads over a range of locations. However, as the number of wave functions in the superposition increases, the wave packet becomes sharper on account of the more complete interference between the positive and negative regions of individual waves. When an infinite number of components are used, the wave packet is a sharp, infinitely narrow spike, which corresponds to perfect localization of a particle. Now the particle is super localized. However, we have lost all information about its momentum. Because the measurement of the momentum will give a result corresponding to any one of the infinite number of waves in the superposition, and which one it will give is unpredictable. Postulate 5. Hence, if we know the location of the particle precisely, implying that its wave function is a superposition of an infinite number of momentum eigenfunctions, then its momentum is completely unpredictable. The conclusion that the line momentum and position of the particle cannot be known simultaneously is summarized by Heisenberg's uncertainty principle, proposed by Werner Heisenberg in 1927. Okay, it is possible to specify simultaneously with arbitrary precision both the momentum and the position of a particle. Heisenberg was able to go beyond this qualitative statement and give the principle a precise quantitative form. Okay. In this expression, delta P is the uncertainty in the line of momentum parallel to the axis K. It's the line of momentum parallel to the axis Q, and delta Q is the uncertainty position along the axis. These uncertainties are precisely defined, for they are the root mean square deviations of the properties from their mean values. If there is a complete certainty about the position of a particle, then the only way that equation 8.2 can be satisfied is for delta P, which implies a complete uncertainty about the momentum. Conversely, if the momentum parallel to an axis is known exactly, delta P equals 0, then the position along the axis must be completely uncertain. Delta Q. The P and Q that appear in equation 8.2 refer to the same direction in space. Therefore, whereas simultaneous specification of the position on the x-axis and the momentum parallel to the x-axis are restricted by the uncertainty relation. Simultaneous location of the position on x and momentum parallel to y or z are not restricted. Table 8.1 summarizes the restriction that the uncertainty principle implies. Okay. Commutation and complementary. The Heisenberg uncertainty principle is a special case of a very general form of an uncertainty principle developed by H.P. Robinson in 1929. The latter applies to any pair of observables called complementary observables, which are defined in terms of the properties of their operators. Specifically, two observable omega 1 and omega 2 are complementary if when the effect of two operators depends on their order, as this equation implies, we say that they do not commute. The different outcomes of the effect of applying omega hat 1 and omega hat 2 in a different order is expressed by introducing the commutator of the two operators, which is defined as this. If the two operators do commute, then the commutator is 0. We can conclude from calculation in example 8.2 that the commutator of the operators for position and line of momentum parallel to the same axis is commutator of position and line of momentum, which similar expression for other axes. This commutator is of such vital significance in quantum mechanics that it is taken as a fundamental distinction between classical mechanics and quantum mechanics. In fact, rather than giving the explicit forms of the operators for position and line of momentum in topic 6, which could have stated postulate 3 as for every observable property omega of a system, there is a corresponding Hermitian operator built from position and line momentum operators that satisfy the communication relation in equation 8.6. which the concept of the commutator establishes. The most general form of the uncertainty principle can be given. For any two pairs of observables, omega 1 and omega 2, the uncertainties to be precise, the root mean square deviations of the values from the mean in simultaneous determination are related by. This is the uncertainty principle in the general form, where the modulus notation means to take the magnitude of the term the bars enclose. The modulus ensures that the product of uncertainties has a real non-negative value. When we identify the observables in equation 8.7 with x and px and use equation 8.6 for the commutator, we obtain equation 8.2, the specific case of the uncertainty principle for position and momentum. Ouch. Okay, the checklist of concepts. The Heisenberg uncertainty principle states that it is possible to specify simultaneously with arbitrary precision both the momentum and the position of the particle. Two observables are complementary if the corresponding operators do not commute. The general form of uncertainty principle provides a quantitative measure of or ability to specify precisely and simultaneously any two observable. Okay, so we have the equation right here, and yeah. Okay. Translational motion in one dimension. What do you need to know already? You should know. Yeah, okay, nobody cares about you, brother. The topic presents the essential features of the solution of Schrodinger equation for one of the basic type for motivation, named translation, blah, 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 blah. Nobody cares. Okay, free motion. Free motion. The Schrodinger equation for the particle of mass m moving in one dimension is this monstrosity. For a particle that is moving in the absence of any external forces, the potential energy is a constant, which can be chosen to be zero. The equation therefore becomes this one. The general solution of these equations are these one. Okay. With A and B constant, as may be verified by substitution. Note that we are now labeling both the wave function and the energies, that is the eigenfunction of eigenvalues of the Hamilton operator H, with the index k. The wave function in equation 9.3 are continuous and have continuous slope everywhere, are single value, and do not go to infinity, and so in the absence of any other information are acceptable for all values of k. Because the energy of the particle is proportional to k2, all values of energy are permitted. It follows that the translation energy of a free particle is quantized. The values of a consistent A and B depend on how the state of motion of a particle is prepared. If it's not shot towards positive x, then its linear momentum is plus k bar h, and its wave function is proportional to eikx. In this case, b was 0 and a is a normalization factor. If it's shot in the opposite direction towards negative x, then the linear momentum is minus kh bar, and its wave function is proportional to e minus ikx. In this case, a equals 0 and b is the normalization factor. Although the wave function is for a free particle, e plus minus ikx is not square integrable in the region of infinite length. The conjugate wave function times the wave function is a constant, and its integral all over space and therefore infinite. We can get around this problem by assuming that the particle is in an infinite region of length L. L from Death Note. Normalizing the wave function and then the end of any subsequent calculation using the wave function, allowing L to become infinite. See problem 9.5. About the location of a particle, to conclusion is consistent with the uncertainty principle, because if the momentum is certain, the position cannot be specified. The operators corresponding to x and p do not commute, and thus correspond to complementary opposite variable. A final point in this connection is that the wave function of e ikx and e minus ikx illustrate a general feature of quantum mechanics. A particle with a net motion is described by a complex wave function, complex in the sense of depending on I equals minus 1 in half, and having both real and imaginary parts. A wave function that is purely real corresponds to zero net motion. For instance, if psi x equals cosinus kx, then the expectation value of a line of momentum is 0p. Okay. Confined motion, the particle in a box. In this section, we consider a particle in a box, in which a particle of mass m is confined to a finite region of space between the two impenetrable walls. The potential energy is 0 inside the box, but raises abruptly to infinitely at the walls x0 and xl. The potential energy of the particle is given by, for x is smaller than 0, and okay. Okay. When the particle is between the walls, the Schrodinger equation is the same as for a free particle. So the general solution given in equation 9.3 are also the same. However, it will prove a convention convention is to use e plus minus ikx equals cos x kx plus minus I sin really kx2 particle in the box in a 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 box. What in the hell is this? Oh my god. Maybe quantum mechanics was a mistake. Like, why do we need to learn about quantum mechanics? The probability density psi modulus uniform of the particle is in either of pure momentum states I e minus kx or e minus I kx. According to the Born interpretation, topic 5, nothing further can be said. LOL! If we write C equals A minus B, I and D equals A plus B in the general solution take the form. Oh. Oh my god. Wave function k x equals c sinus kx plus d cosinus kx. At the walls and the outside of the box, the wave function must be zero, as the particle will not be found in a region where its positional energy is infinite. Okay, at this point, there are no restrictions on the value of k, and all solutions appear to be acceptable. The acceptable solutions. The requirement of the continuity of the wave function, topic 5, implies that the wave function kx, as given by equation 9.4, must be zero at all walls, for it must match the wave function inside the material of the wall where the function meet. That is, the wave function must satisfy the following two boundary conditions: the constraints on the function at certain locations. As we show in the following justification, the requirement that the wave function satisfy these boundary conditions implies that only certain wave functions are acceptable, and that the only permitted wave function and energies of the particle is R is Oh, okay. Okay, where C is an as yet undetermined constant. Note that the wave function and energy are now labeled with the dimensionless integer n instead of constant k. Dun dun dun. Oh, that's whole justification. Okay. Properties of the wave functions. Figure 9.4 shows some of the wave function of a particle in a one-dimensional box. There are all sine functions with the same amplitude but different wavelengths. Shortening the wavelength will result in a sharper average curvature of the wave function and therefore an increase in the kinetic energy of a particle. Its only source of energy because V is 0 inside the box. Note that the number of nodes, which are points where the wave function passes through 0, not really reaching 0 as the walls, also increases as n increases, and that the wave function as n minus 1 nodes, increasing the number of nodes between walls of a given separation increases the average curvature of the wave function and hence the kinetic energy of the particle. As we've seen, the energies and the wave function are labeled with the quantum number n. A quantum number is an integer. In some cases, if we see topic 19 as a half integer, the label of state of the system for a particle in a one-dimensional box, there are an infinite number of acceptable solutions. Oh, sorry. And the quantum number n specified the one interest. As well as acting as a label, a quantum number can often be used to calculate the energy corresponding to the state of, oh, I went British there, to write the probability density with psi x, no, sorry, psi squared x becomes more uniform as n increases, provided we ignore the fine detail of increasingly rapid oscillations. The probability density at high quantum numbers reflects the classical result that a particle bouncing between the walls spins on average equal times at all points. That the quantum result corresponds to the classical prediction at high quantum numbers is an illustration of a correspondence principle, which states the classical mechanics emerges from quantum mechanics as high quantum numbers are reached. The probability density for a particle in a one-dimensional box is blah 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 blah. Okay, this one fancy formula, and varies with position. The non-uniformity in the probability density is pronounced when n is small. The most probable location of a particle corresponds to the maxima in the probability density. The properties of observable. The linear momentum of a particle in a box is not well defined because the wave function sinus kx is not an eigenfunction of the linear momentum operator. However, each wave function is a linear combination of a linear momentum eigenfunction e ikx and e minus ikx. Then, because sinus x equals e ix minus e minus ix equals 2i, we can write this lowest, no, we can write so this is what we write. If follows topic 7, the measurement of the line momentum will give the value plus k8 bar for healthy measurement of momentum and minus k bar h bar for other half. This detection of opposite directions of travel with equal probability is the quantum mechanical version of the classical picture that a particle in a one-dimensional box rattles from wall to wall and in any given period spends half its time traveling to the left and half traveling to the right. Because n cannot be zero, the lowest energy and the particle may possess is not zero, as will be allowed by classical mechanics corresponding to stationary particle. But what? This lowest irremovable energy is called zero-point energy. The physical origin of a zero-point energy can be explained by in two ways. The Heisenberg uncertainty principle requires a particle that possesses kinetic energy if it's confined to an infinite region. The location of a particle is not completely indefinite, so the uncertainty in its momentum cannot be precisely zero. Because all of this implies that this is not zero, which implies the particle must always have non-zero kinetic energy. The wave function is to be zero at the walls, but smooth, continuous, and not zero anywhere. Then it must be curved, and curvature in the wave function implies the position of a kinetic energy. The separation between adjacent energy levels with quantum numbers n plus 1 is all of this. This separation decreases as the length of a container increases and is very small when the container has macroscopic dimensions. The separation of adjacent levels becomes zero when the walls are infinitely far apart. Atoms and molecules free to move in normal laboratory-sized vessels may therefore be treated as though their translational energy is not quantized. The translational energy of a free particle is not quantized. A particle with net motion is described by a complex wave function. A real wave function corresponds to zero net motion. The need to satisfy boundary conditions implies that the only certain wave functions are acceptable and therefore restrict observable to discrete values. A quantum number is an integer. In certain cases, a half integer that labels the state of the system. Notes a point where the wave function passes through zero. A particle in a box possesses a zero-point energy. The corresponding principle states that classical mechanics emerges from the quantum mechanics as high quantum numbers reached. Alright, I think I don't need to read more, right? Yeah, I don't need to read more. I think it's enough. It's enough. It's enough. Alright, cool. Now I got my quantum mechanics homework in check. Now I have to read about NMR. I don't understand this shit, honestly. I really don't. Like, it's annoying me so bad. Like, so bad. But it feels good to do my reading homework with you guys. No, I'm getting very productive every time I stream. Like, I do my shit. Okay, let me... Give me a moment. Oh, I hope you're all having a wonderful day. And yeah. This should probably. You can probably see my screen, right? Let's make it a little more. Just boom. There we go. Now let's get this shit on the road, baby. Let's understand what the hell NMR is, because I really need to understand what the hell I'm dealing with. Let's go! Nuclear magnetic resonance, NMR spectroscopy, is the most useful technique for structure determination that you will encounter in your textbook. Analysis of NMR spectrum provides information about how the individual carbon and hydrogen atoms are connected to each other in the molecule. This information enables all these quantum mechanics words are really tongue twisted my tongue. Can't even read basic English anymore. This information enables to us to determine the carbon-hydrogen framework of a compound. I got the hiccups also, thank you. Much the way puzzle pieces can be assembled in the form of a picture. Your textbook will provide an explanation of the theoretical underpinnings of NMR spectroscopy. How it works, here's a brief summary. The nucleus of a hydrogen atom, which is just a proton, possesses a property called nuclear spin. A true understanding of this property is beyond the scope of a course, so we will think of it just as a rotating sphere of charge, which generates a magnetic field called the magnetic moment, which, when the nucleus of a hydrogen atom is subjected to an external magnetic field, the magnetic moment can be aligned either with the field called the alpha spin state or against the field called the beta spin state. There are differences in energy, delta E, between these two spin states. If a proton occupying a alpha spin state is subjected to electromagnetic radiation, an absorption can take place. If the energy of the proton is equivalent to the energy gap between the spin states, the absorption causes the nucleus to flint on the beta spin state, and the nucleus is said to be in a resonance. Thus, the term nuclear magnetic resonance, NMR. Okay, NMR spectrometers employ strong magnetic fields, and the frequency of the radiation typically required for a nuclear resonance falls in the radio wave region of electromagnetic spectrum called RF radiation. As at a particular magnetic field strength, we might expect all nuclei to absorb the same frequency of RF radiation. Hopefully, when I understand spectroscopy, like so good, then I will make a video to you guys, because right now I don't understand shit. And maybe also I want to make a video about quantum mechanics, like a little video about that too. Like in simple terms, that would be pretty cool. But for now, let's just pass this course, alright? NMR spectrometers employ strong magnetic field. Where was I? At a particular magnetic field strength, we might expect all nuclei to absorb the same frequency or RF radiation. Luckily, this is not the case, as the nuclei are surrounded by electrons. In the presence of an external magnetic field, the electron density circulates, establishing a small local magnetic field that shields the proton. Not all protons occupy identical electronic environments. Some protons are surrounded by more electron density and are more shielded, while other protons are surrounded by less electron density and are less shielded or de-shielded. As a result, protons in different electric environments will absorb a different frequency or RF radiation. This allows us to probe the electronic environment of the hydrogen atoms in a compound. Chemical equivalence. The spectrum produced by HNMR spectroscopy, pronounced proton NMR spectroscopy, is called proton NMR spectrum. Here's an example. Okay, yeah, cool. I've seen this before. The first valuable piece of information is the number of signals. The spectrum above has 3 different signals. In addition, each signal has the following important characteristic. 1. The location of each signal indicates the electronic environment of the protons giving rise to the signal. 2. The area under each signal indicates the number of protons giving rise to the signal. 3. The shape of the signal indicates the number of neighboring protons. We will discuss these characteristics in the upcoming section, but first let's explore the... Okay, you want it to be black? First, let's explore the information that is revealed by counting the number of signals in the spectrum. The number of signals in a proton NMR spectrum indicates the number of different kinds of protons in different electronic environments. Protons that occupy identical electronic environments are called chemically equivalent, and they will produce only one signal. 2 protons are chemically equivalent if they can be interchanged by symmetry operation. Your textbook will likely provide a detailed explanation. With examples, for our purposes, the following simple rules can guide you in most cases. The 2 protons of CH2 group will generally be chemically equivalent if the compound lacks chiral centers. But if the compound has a chiral center, then the protons of a CH2 group will generally not be chemically equivalent. Okay, so these 2 protons are chemically equivalent and these 2 protons are not chemically equivalent. The 2 CH2 groups will be equivalent to each other, giving 4 equivalent protons if the CH2 groups can be interchanged by either rotation or reflection. Example, these 4 protons are chemically equivalent. The previous rule also applies for CH3 groups or CH groups. Here are some examples. These 6 protons are chemically equivalent. These 2 protons are chemically equivalent. The 3 protons of a methyl group are always chemically equivalent, even if there are chiral centers in the compound. These 3 protons are chemically equivalent. For aromatic compounds, it will be less confusing if you draw a circle in the ring, rather than drawing alternating pi bonds. For example, the following methyl-2 methyl groups are equivalent, which can be easily seen when drawn in the following way. Identify the number of signals expected in the HNMR spectrum of the following compound. Let's begin with the 2 methyl group on the center of the compound. These 2 methyl groups are equivalent to each other because they can be interchanged by either rotation or reflection. Only one type of symmetry is necessary, but in this case we have both reflection and rotation. So these 6 protons are certainly chemically equivalent. We therefore expect one signal for all 6 protons. Now let's consider the following methylene CH2 groups. For each these methylene groups, the 2 protons are chemically equivalent because there are no chiral centers. In addition, these 2 methylene groups will be equivalent to each other since they can be interchanged by rotation or reflection. We therefore expect one signal for all 4 protons. The same argument applies for the following 2 methylene groups. These 4 protons are chemically equivalent, but they are a different form from the other methylene groups in the compound because they cannot be interchanged with any of the other methylene groups via rotation or reflection. In similar ways, the following 4 protons are chemically equivalent. The following 4 are also currently. So with respect to protein NMR spectrum of this compound has 6 signals. Chemical shift, baby. Here we go. We will now begin exploring the 3 characteristics of every signal in an NMR spectrum. The first characteristic is the location of the signal, called its chemical shift, delta, which is defined relative to the frequency of absorption of a reference compound, tetramethylsilane, TMS. Okay, cool. I got like a... Ouch, never mind. Your textbook will go into great depth in explaining chemical shift and why it's on the numbers that are reporting part per million per hour. For now, we will simplify point out the most organic compounds the signal produced will fail in a range between 0 and 10 ppm. In rare cases, it is possible to observe a signal occurring at a chemical shift below 0 ppm, which results from a proton that absorbs a lower frequency than the proton in TMS. Most protons in organic compounds absorb a higher frequency than TMS. So all chemical shifts that you encounter in your textbook will be positive numbers. Okay, cool. The left side of an NMR spectrum is described as a downfield, and the right side of the spectrum is described as upfield. So on the right is upfield and on the left is downfield. Okay, but keep in mind that these terms are used in a relative way. For example, we should say that the signal at 2.5 ppm in the spectrum above 2.5 ppm, there's nothing on the 2.5 ppm, is downfield from the signal at 2.5, yeah, okay, I see 2.5 right here and 2.2, yeah. Similarly, the signal at a 6.8 ppm is upfield from a signal at 7.1 ppm. The process of alkanes typically produce signals between 1 and 2 ppm. We can now explore some of the effects that can push out a signal downfield relative to a position of an alkane. Recall their electronegative atoms, such as halogens, withdraw electron density from neighboring atoms. Okay, the inductive effect causes the neighboring protons to be de-shielded, surrounded by less electron density. And as a result, the signal produced by these protons is shifted downfield. That is, the signal appears at a higher chemical shift than the protons of an alkane. The strength of this effect depends on the electronegativity of a halogen. Compare the chemical shift of the protons in the following compounds. Okay, so the larger ppm, then they have a more electronegative halogen. Okay. Fluorine is the most electronegative element and therefore produces a stronger effect. When multiple halogens are present, the effect is generally additive, as can be seen when comparing the following compound. Okay, the more halogens then. Each chlorine atom adds approximately 2 ppm to the chemical shift of the signal. An important aspect of inductive effects is that the fact that they taper off drastically with distance, as can be seen by comparing the chemical shift of the protons in the following compound. Okay. The effect, oh yeah, I see the chlorine. Okay. The effect is more significant for the protons of the alpha A position. The protons at the B beta position are only slightly affected, and the protons at the gamma position are virtually unaffected by presence of the chlorine atom. By committing a few numbers to memory, you should be able to predict the chemical shift for a proton in a wide variety of compounds, including alcohols, ethers, ketones, esters, and carboxylic acids. The following numbers can be used as benchmark values. Okay. In the absence of inductive effects, a methyl group CH3 is generally produce a signal near 0.9 ppm. A methylene group CH2 will produce a signal near 1.2 ppm. And a methine group CH will produce a signal near 1.7 ppm. These benchmark values are then modified by presence of neighboring functional groups in the following way. Okay, so oxygen, a functional group of oxygen of an alcohol or ether. So a methylene group, so 3.7 ppm. Oxygen of an alcohol or ether. Oxygen of an ester, 4.2 ppm. A carbonyl group to 2.2 ppm. The values above represent the effect of a few functional groups on the chemical shift of the alpha protons. The effect on beta protons is generally about 1/5 of the effect on the alpha protons. For example, in alcohol, the presence of an oxygen atom adds plus 2.5 ppm to a chemical shift of alpha protons, but adds only 0.5 ppm to the beta protons. Similarly, a carbonyl group adds plus 1 ppm to the chemical shift of the alpha protons, but only to plus 0.2 to the beta protons. The values above, together with the benchmark values for methyl, methylene, and methine groups, enable us to predict the chemical shift for protons in a wide variety of compounds. Let's see an example. Predict the chemical shift of the signal in the proton NMR spectrum for the following compound. First, determine the total number of expected signal. In this compound, there are 4 different kinds of protons, giving rise to 4 distinct signals. For each type of signal, identify whether it represents methyl, methylene, or methine. Okay. Finally, modify each of these numbers based on proximity to the oxygen and the carbonyl group. Okay. These values are only estimates, and the actual chemical shift might differ from the predicted values. Note that the methane proton, we did not count the distant C-double-O bond and add plus 0.2 because the ester group is considered as one group, which has the effect of adding plus 3.0 to the chemical shift of the methane proton. Similarly, note that the methylene protons, we did not add plus 0.5 for a distant oxygen. Once again, the ester group is considered as one group, which has been effect of adding plus 10 plus 1.0 to the chemical shift of the methylene protons. Okay, cool. The chemical shift of the proton is also sensitive to the presence of nearby pi electrons. This effect is particularly strong for aromatic protons. Protons connect directly to an aromatic ring. In your textbook, you will find diagrams showing how and why the aromatic protons are affected. Here's a brief summary. The external magnetic field causes the pi electrons to circulate, and this flow of electrons causes an induced local magnetic field. The aromatic protons experience not only the external magnetic field, but they also experience the induced local magnetic field. As a result, aromatic protons feel a stronger net magnetic field, which causes the signals to be shifted downfield significantly. In fact, aromatic protons generally produce signals in the neighborhood of 7 ppm, sometimes higher as 8 ppm, sometimes as low as 6.5 ppm in the NMR spectrum. For example, consider the structure of ethylbenzene. Ethylbenzene has 3 different kinds of aromatic protons. Make sure you can identify them. Producing 3 overlapping signals just above 7 ppm, a complex set of overlapping signals around 7 ppm is characteristic of compounds with aromatic protons. A methylene group CH2 is in ethylbenzene produces a signal at 2.6 ppm rather than the expected benchmark value of 1.2 ppm. These protons have been shifted downfield because of their proximity to the aromatic ring. They are not shifted as much as aromatic protons in themselves because the methylene protons are further away from the ring, but there is still a noticeable effect. All pi electrons, whether they belong to an aromatic ring or not, have an effect on neighboring protons. For each type of pi bond, there are precise locations of nearby protons determine their chemical shift. For example, aldehydic protons produce characteristic signals at approximately 10 ppm. Below are some important chemical shifts. It should be wise to become familiar with these numbers, as they will be required in order to interpret proton NMR spectra. Okay, so this is basically our bread and butter. So a methyl has a chemical shift or ppm on 0.9. A methylene, a CH2 group, has 1.2. A methine group has a 1.7. Allylic has a 2. Alkenyl has a 2.5. Benzylic methyl has a 2.5. Alkyl halide has a 2 to 4. Alcohol has 2 to 5. Vinylic has a 5.4.5, 6.5. Aryl has a 6.5 to 8. Aldehyde has a 10 ppm. Carboxylic acid has a 12 ppm. Integration. In the previous section, we learned about the first characteristic of every signal. Chemical shift. In this section, we will explore the second characteristic, integration, which is the area under each signal. This value indicates the number of protons given rise to a signal. After acquiring a spectrum, a computer calculates the area under each signal and then displays this area as a numerical value placed under the signal. Thus, these numbers only have meaning when compared to each other. In order to convert these numbers into useful information, choose the smallest number. Okay, the smallest number, 27.0 in this case, and divide all the integration values by this number. Okay, these numbers provide the relative number or ratio of protons giving rise to each signal. This means that a signal with integration of 1.5 involves 1.5 times as many protons as a signal with an integration of 1. In order to arrive at the whole number, there is no such thing as a half proton. Multiply all the numbers above by 2, giving the same ratio now expressed in whole numbers. So it's going to be 2.3.2.3. In other words, the signal at 2.4 ppm represents 2 equivalent protons, and the signal at 2.1 represent 3 equivalent protons. Integration values are often represented by step curves. For example, yeah, I've seen this. So this is a integral in NMR. The height of each step curve represents the area under the signal. In this case, a comparison of the heights of the 4 step curves reveals a ratio of 2:3:3. When interpreting integration values, don't forget the numbers are only relative. For example, consider the structure of butane. Butane has 2 kinds of protons and will therefore produce 2 signals in its proton NMR spectrum. The methyl groups give rise to 1 signal and the methylene groups give other signal. On computer analysis, the area under each signal provides numbers that allows us to calculate the ratio of 2.3 or 2 of 3. This ratio only indicates the relative number of protons giving rise to each signal, not the exact number of protons. In this case, the exact numbers are 4 for methylene groups and 6 for methyl groups. When analyzing the wait, what? Okay. When analyzing the nMOL spectrum of an unknown compound, the molecular formula provides extremely useful information because it enables us to determine the exact number of protons giving rise to each signal. If we were analyzing the spectrum of butane, the molecular formula C4H10 will indicate that the compound has a total of 10 protons. This information then allows us to determine the ratio of 2:3 must correspond with 4 protons and 6 protons in order to give a total of 10 protons. The previous example illustrated the important role that symmetry can play when considering integration values. Here's another example. This compound has only 2 kinds of protons because 2 methylene groups are equivalent to each other and 2 methyl groups are equivalent to each other. The proton NMR spectrum is therefore expected to exhibit only 2 signals with relative integration values of 2 and 3. But once again, the values 2 and 3 are just relative numbers. They actually represent 4 protons and 6 protons. This can be determined by inspecting the molecular formula C4H10O, which indicates a total of 10 protons in the compound. Since the ratio of protons is 2.3, this ratio must represent 4 and 6 protons in order for the total number of protons to be 10. Okay, so exercise. A compound with a molecular formula C5H10O2 has the following proton NMR spectrum. Determine the number of protons to give each signal. Spectrum has 3 signals. Begin by combining the relative values. 6.7. So take the lowest number and divide it by this, right? The smallest number, yeah. And divide it. This gives us a ratio of 1:3:6, but these are just relative numbers. To determine the exact number of protons given rise to each signal, look at the molecular formula, which indicates a total of 10 protons in the compound. Therefore, the numbers 1:3:6 are not only relative values, but they also the exact value. Exact integration values are sometimes expressed in the following ways. Oh shit. Multiplicity. Come on, let's go. The third and final characteristic of each signal is its multiplicity. Multiplicity, which refers to the number of peaks in the signal. A singlet has 1 peak, a doublet has 2 peaks, a triplet has 3 peaks, a quartet has 4 peaks, a quintet has 5 peaks, etc. The multiplicity of a signal is the result of magnetic effect of the neighboring protons, and therefore indicates the number of the neighboring protons. Your textbook will explain the cause of this effect in detail. The net effect can be summarized with the n+1 rule, which states the following. If n is the number of neighboring protons, then the multiplicity will be n plus 1. For example, a proton with 3 neighbors, n equals 3, will be split into a quarter. N plus 1 equals 3 plus 1 equals 4 peaks. It is important to realize that nearby protons do not always split each other. There are two major factors that determine whether or not splitting occurs. 1. Equivalent protons do not split each other. Consider that two methylene groups in the following compound. No splitting. All 4 protons are chemically equivalent, and therefore they do not split each other. Instead, they produce one signal that has no neighboring protons, N0. So the signal is a singlet. In order for splitting to occur, the neighboring protons must be different than the protons producing the signal. Splitting is most commonly observed when protons are separated by either 2 of 3 sigma bonds. So non-equivalent protons separated by 2 sigma bonds, or non-equivalent protons separated by 2 sigma bonds. However, when 2 protons are separated by more than 3 sigma bonds, splitting is generally not observed. 2-4 report. Such long-range splitting is only observed in rigid molecules, such as bicyclic compounds, or in molecules that contain rigid structures, such as allylic systems. For purposes of this introductory treatment of NMR spectra, we will avoid examples that exhibit substantial long-range splitting. Make sure to look through your lecture notes to see if any example of long-range splitting are included. Determine the multiplicity of each signal in expected proton NMR spectrum of the following molecule. Begin by identifying the different kind of proton that is determine the number of expected signals. Okay, so we have 3 equivalent methyl groups. Methyl group or methylene group? This compound is expected to produce 3 signals in its proton NMR spectrum. Now, let's analyze each signal using the n plus 1 rule. Singlet, triplet, quartet, yeah. Notice that the third butyl group on the left side of the molecule appears to be a singlet because the following compound atom has no protons. The quaternary compound atom is directly connected to each of the 3 neighboring methyl groups, and as a result, each of the 3 methyl groups has no neighboring protons. This is characteristic of a third butyl group. When signal splitting occurs, the distance between the individual of the signal is called coupling constant or J value, and is measured in hertz. Neighboring protons always split each other with equal J values. For example, consider the 2 kinds of protons in an ethyl group. Okay. The HA signal is split into a quartet under influence of 3 neighbors. The HB signal is split into a triplet under influence of its 2 neighbors. HA and HB are said to be coupled to each other. The coupling constant JAB is the same for each proton, so the spacing between peaks is the same as both signals. Okay, pattern recognition. Now we're getting to the spicy good part. Finally. There are a few splitting patterns that are commonly seen in proton NMR spectrum. And you will save yourself time on the exam if you can recognize these patterns. An ethyl group is characterized by a triplet with an integration of 3. Okay. And a quartet with an integration 2, an isopropyl group is characterized by a duplet with an integration 6 and a septet with an integration 1. A terbutyl, okay. lower. Complex splitting occurs when a proton has two different kinds of neighboring protons. For example, consider the splitting pattern that you might expect for the highlighted proton, Hb, in the following compound. In this case, Hb has two different kinds of neighbors. There is one Ha proton to the left and there are two Ac protons to the right. As a result, the signal of Hb is being split into duplet because of a nearby Ha proton, and is also being split into triplet because of a nearby Hc proton. The signal is therefore expected to have 6 peaks. The shape multiplicity of this signal depends greatly on the J values. In this case, JAB is much greater than JBZ, so the signal appears as a duplet of triplets, as shown in the following splitting frame. Alright. This splitting free shows the signal of Hb being split into a duplet by one neighboring proton, Ha, and then each peak of its duplet is further split into a triplet by its neighboring Ac protons. The result is two triplets spaced very closely next to each other in the spectrum, and this pattern is called a duplet of triplets as shown above. This splitting pattern is a result of the fact that these spatial arrangement between Hb and HA is very different than the spatial arrangement between Hb and Hc. So JAB is much greater than JBC. Now, let's consider a case in which J values are more similar. An example, consider the two Hb protons highlighted in the following compound. This structure lacks the rigid double bond that was in the previous example, and in such case where the compound has only one single bond, that are all experience free rotation. All the J values will generally be similar, nearly 7 Hz. The Hb protons have two different types of neighbors. There is one neighbor to the left, Ha, which should be split the signal into a duplet, and there are three neighbors, Hc, to the right, which should split the signal into a quartet. Therefore what? Therefore, we might have expected either a double or a quartet of double duplets if there had been a large difference between J values and JAB and JBC. However, in this case, we have pointed out that J values are extremely similar. JAB is almost JAC, 7 Hz. And in such case, we do not observe the complex splitting. Rather, the Hb protons are considered to have 4 neighbors. And according to the n+1 rule, the signal of the Hb protons will be quintet. n+1 equals 4 plus 1 equals 5 is quintet. This outcome can be justified by the following splitting free. This splitting free tree shows the signal for the Hb proton being split into quartet by the numbering Hc protons, and then each peak of the quartet is further split into duplet by a neighboring Ha proton. Since JAB equals JAC, the peaks of the signal end up overlapping perfectly to produce a signal with exactly 5 peaks, a quintet. Note that we can get the same result at quintet if we draw a splitting free tree where I got the hiccups. Where we first split the signal into a duplet and then split each of the two peaks into I got the hiccups. Of the two peaks of the duplet into a quartet. The signal is a quintet because JAB equals JAC. In case of a previous examples, we have seen how the multiplicity of a signal in its shape depends greatly on the J values. We saw a case where a J value were very different from each other, giving rise to complex splitting. And we also saw a case where J values are extremely similar, in which case complex splitting was not observed. Finally, let's consider what will be the case if J values are similar but not identical. In such a case, the peaks do not overlap nicely, and the result can be a signal that is difficult to analyze. This type of signal is called a multiplet. An example of multiplet is shown below. No splitting. In the previous section, we saw an example of complex splitting. Now, in this section, we will explore cases where there is no splitting at all, despite the presence of neighboring protons. Consider the proton NMR spectrum of ethanol. As expected, the spectrum exhibits the characteristic a signal of the ethyl group, a quartet with integration of 2 and a triplet with an integration of 3. In addition, there is also a signal at 2.2 ppm representing the hydroxyl proton OH. Hydroxyl protons especially produce a signal between 2 and 5 ppm, and it is often difficult to predict exactly where the signal will appear. In the proton NMR spectrum above, notice that the hydroxyl proton is not split into a triplet form from the neighboring methylene group. Generally, no splitting is observed across the oxygen of an alcohol, because proton exchange is a very rapid process that is catalyzed by trace amount of acid or base. So the water attacks the OH attacks the water, then jumps back to the O, and then the water attacks the proton, then the proton connects to the okay. Hydroxyl protons are said to be labile because the rapid rate of which their exchange. This proton transfer process occurs at a faster rate than the timescale of an NMR spectrometer, producing a blurry effect that averages out any possible splitting effect. It is possible to slow down the rate of proton transfer by scrupulously. Okay, that word is on vacation. Removing the trace amounts of acid and base dissolved in ethanol. Such purified ethanol does in fact exhibit splitting across the oxygen atom. So the signal at 2.2 ppm is observed to be a triplet, and the signal at 3.7 ppm is observed to be a quintet. So N equals 4. There is one other common example of neighboring protons that often do not produce observable splitting. Other Heidelberg protons, which generally produce signal near 10 ppm, will often couple only weakly by the neighbors. example, a very small J value. Because the J value is so small, the aldehyde signal near 10 ppm typically appears to be a singlet. Hydrogen deficiency. Oh my! I can't even. Hydrogen, HDI basically. In the previous section of the chapter, we have learned all the individual tools you need to analyzing a proton NMR spectrum. Considering the number of signal analyzing chemical shift, assessing the integration values, interpreting multiplicity of each signal, pattern recognition, etc. Now we're just about ready to put all these two together, but there's one important tool that you will need, and we'll cover the tool in this section. Imagine that you have an unknown compound with a molecular formula of C6H12O. The molecular formula by itself does not provide enough information to draw the structure of the compound. There are many constitutional isomers with a molecular formula C6H12O. Nevertheless, a careful analysis of the molecular formula can often provide helpful clues about the structure of the compound. To see how this works, let's begin by analyzing the molecular formula of several alkanes. Compare the structure of the following alkanes, paying special attention to the number of hydrogen atoms attached to each carbon atom. Okay, cool. We have methane, ethane, propane, and butane. In each case, there are two hydrogen atoms at the end of the structure cellulose, and there are two hydrogen atoms on every carbon atom that can be summarized by this. Okay. Where n is the number of carbon atoms in the compound. Accordingly, the number of hydrogen atoms will be 2n plus 2. In other words, all of the compounds above have a molecular formula of CnH2n plus 2. This is true even for compounds that are branched, rather than being a straight chain. The compounds above are said to be saturated. That is, they possess the maximum number of hydrogen atoms possible relative to the number of carbon atoms present. A compound with a pi bond or double or triple bond can have fewer than maximum number of hydrogen atoms. Such compounds can be said to be unsaturated. Yeah. A compound containing a ring will also have fewer than a maximum number of hydrogen atoms, just like a compound with double bond. For example, compare the structure of 1-hexene and cyclohexane. Both compounds have the molecular formula C6H12 because both are missing two hydrogen atoms. 6 carbon atoms should be able to accommodate 2 times 6 plus 2 equals 14 hydrogen atoms. Each of these compounds is said to have 1 degree of unsaturation. The hydrogen deficiency index, HDI, is a measure of the number of degree of unsaturation. So basically, you use HDI to determine if there's any double bond present in the compound. A compound is said to have 1 degree of unsaturation for every 2 hydrogen atoms that are missing. For example, a compound with the molecular formula C4H6 is missing 4 hydrogen atoms. If saturated, it will be C4H10, so it has 2 degrees of unsaturation, HDR2. There are several ways for a compound to possess 2 degrees of unsaturation. Both double bonds, or 2 rings, or 1 double bond and 1 ring, or 1 double triple bond. Let's explore all the possible. Okay, interesting. These are all the possible constitutional isomers for C4H6. With this in mind, let's expand our skill set. Let's explore how to calculate the HDI when other elements are present in the molecular formula. Halogens. Compare the following two compounds. So we have ethane and chloroethane. Notice that the chlorine takes the part of the hydrogen atom. Therefore, the purpose of calculating the HDI treat a halogen as it were a hydrogen atom. For example, C4H9Cl should be the same HCl as C4H10. So we have oxygen compared to following compounds, ethane and ethanol. Classic. Notice that the presence of oxygen atom does not affect the accepted number R of hydrogen atoms. Therefore, whenever oxygen atom appears in the molecular formula, it should be ignored for purposes of calculating the HDI. For example, C4H8O should have the same HDI as C4H8. Okay, so nitrogen, we have ethane and ethylamine. Notice the presence of a hydrogen atom changes the number of expected hydrogen atoms. It gives one more hydrogen atom than will be expected, highlighted above. Therefore, whenever a nitrogen atom appears in the molecular formula, one hydrogen atom must be subtracted from the molecular formula. For example, C1H9N should have the same HDR as C4H8. In summary, halogens add 1 H for each halogen, oxygen ignore, nitrogen subtract 1 H for each N. These rules will enable you to determine the HDI for most simple compounds. Alternatively, the following formula can be used. Okay, so that's pretty unique. C is the number of carbon atoms, N is the number of nitrogen atoms, and H is the number of hydrogen atoms, and X is the number of halogens. This formula will work for all compounds containing C, H, N, O, and or halogens. Calculating the HDI is particularly helpful because it provides clues that the structural features of the compound. For example, an HDI of 0 indicates the compound cannot have any rings or bonds, or pi bonds. That is extremely useful information when trying to determine the structure of a compound, and it's information that is easily obtained by simply analyzing the molecular formula. Similarly, HDI of 1 indicates that the compound must have either one bond, or one double bond, or one ring, but not both. If the HDI is 2, then there are several possibilities: 2 rings or 2 double bonds, or 1 ring or 1 double bond, or 1 triple bond. Analysis of HDI for an unknown compound can often be a useful tool, but only when the molecular formula is known with certainty. When we use this technique in this next section, the following exercise will be okay. Calculate the HDI for a compound with molecular formula C5H8BR2O2 to identify the source of information provided by the HDI. Answer: use the following calculation. Okay. Yeah, so they got 1. With 1 degree of unsaturation, the compound must contain either 1 ring or 1 double bond, but not both. The compound cannot have a triple bond as they will require 2 degrees of unsaturation. Okay. In this section, we will practice analyzing and interpreting NMR spectrum, a process that involves 4 discrete steps. Analyzing a protein NMR spectrum. In this section, we will practice analyzing and interpreting NMR spectra, a process that involves 4 discrete steps. 1. Always begin by inspecting the molecular formula if it's given, as it provides useful information. Specifically, calculating the hydrogen HCI can provide important clues about the structure of the compound. An HCI of 0 indicates that the compound does not possess any rings or pi bonds. An HCI of 1 indicates the compound has either one ring or one pi bond. An HCI of 4 or more indicates the likely presence of an aromatic ring. Consider the number of signals and integration of each signal that gives the clues of symmetry of the compounds. Analyze each signal, chemical shift, integration, and multiplicity, and then draw fragments consistent with each signal. These fragments become puzzle pieces that must be assembled to produce a molecular structure. Assemble the fragment into a molecular structure. The following exercise illustrates how it's done. Okay. Identify the structure of a compound with molecular formula C9, H10, and O that exhibit the following proton in the Morse spectrum. Okay. So when we have the formula, then we have to use the HDI. The first step is to calculate the HDI. The molecular formula indicates 9 carbon atoms, which require 10 hydrogen atoms in order to be fully saturated. There are only 10 hydrogen atoms, which means that 10 hydrogen atoms are missing, and therefore the HCI is 5. This is a large number, and it will be not efficient to, because also when it's over 7, it's an aromatic ring. It's a large number, and it will be not efficient to think about the possibility of having 5 degrees of unsaturation. However, anytime we get an HCI of 4 or more, we should be on the lookout for aromatic ring. Yeah, you can also see it when it's above 7 ppm. We must keep this in mind when analyzing the spectrum. We should expect the aromatic ring HCI 4 plus one other degree of unsaturation, whatever a ring or a double bond. The second step is to consider the number of signals at the integration value of each signal. In this spectrum, we see 4 signals. In order to analyze the integration of each signal, we must divide by the lowest number. Okay. So the ratio is 1:5:2:2. Now, look at the molecular formula. There are 10 protons in the compound, so the relative integration values represent the actual number of protons giving rise to each signal. Yeah. Okay. Next step is to analyze each signal. Starting upfield. Okay, so they start here. No, they start here. Upfield. Oh yeah, upfield. Right, D shield is more or left. Okay. Starting upfield, there are 2 triplets. Is that a triplet? Yeah, one triplets. Each with integration of 2. This suggests that there are 2 adjacent methylene groups. Okay. These signals do not appear at 1.2 with methylene groups are expected. So one or more factors is shifting these signals downfield. Our proposed structure must take that into account. Moving more down shield through the spectrum, the next signal appears just above 7 ppm, characteristic of aromatic protons, just as we suspected after analyzing the HDI. The multiplicity of aromatic protons only rarely gives useful information. More often, a messy multiplet of overlapping signals is observed, but the integration value gives important information. Specifically, there are 5 aromatic protons, which means that the aromatic ring is monosubstituted. Moving on to the last signal, we see a signal of 10 ppm with an integration of 1. This is suggested aldehydic proton. In summary, our analysis has produced the following fragments. Okay. ppm of 10. The final step is to assemble these fragments. Fortunately, there's only one way to assemble these 3 puzzle pieces. Boom. We mentioned before that each methylene group is being shifted downfield by one or more factors. Our proposed structure explains the observed chemical shifts. In particular, one methylene group is shifted significantly by carbonyl group and slightly by the aromatic ring. The other methylene group is being shifted significantly by the aromatic ring and slightly by the carbonyl group. Okay, CNMR spectroscopy. Many of the principles that apply to NMR spectroscopy also apply to CNMR spectroscopy. But there are a few major differences, and we will focus on those. For example, H1H is the most abundant isotope of the hydrogen, but 13C is only a minor isotope of carbon, representing about 1.1% of all carbon atoms found in nature. As a result, only one of every 100 carbon atoms will resonate, which demands the use of sensitive receiver coil for 13 CNMR. In HNMR spectroscopy, we saw that each signal has three characteristics: chemical shift, integration, and multiplicity. In CNMR spectroscopy, only the chemical shift is important. The integration of multiplicity of seasons are typically not observed, which greatly simplifies the interpretation of CNMR spectra. Integration values are not routinely calculated in CNMR spectroscopy because the pulse technique employed by NMR spectrometers has been undesired effect by distorting the integration values, rendering them useless in most cases. Multiplicity is also not a common characteristic of typical CNMR experiments. Notice that all of the signals are observed as singlets. This is a result of a special technique called broadband decoupling that processes all 13C and 1H splitting. If we did not use this technique, then the signal of each 13C atom nucleus will be split not only by the protons directly connected to it, separated by only one sigma bond, but it will also be split by the protons that are 2 or 3 sigma bonds removed. This will lead to a very complex splitting patterns, and the signal will overlap to produce an unreadable spectrum. The use of broadband decoupling causes all the 13C signals to collapse to singlets, which renders the spectrum more easily interpreted. In CNMR spectroscopy, chemical shift values typically range from 0 to 220 ppm. The number of signals in CNMR spectrum represent the number of carbon atoms in the different electronic environments, not interchangeable by symmetry. Carbon atoms that are interchangeable by symmetry, either rotation or reflection, will only produce one signal. To illustrate this point, consider the compounds below. Each compound has 8 carbon atoms, but does not produce H signals. The equivalent carbon atom is each compound are labeled with the same letter. Okay. The location of each signal is dependent on shielding and deshielding effects, just as we saw in proton and NMR spectroscopy. Below a chemical shift, there are several important types of carbon atoms. Okay, so when it's above 0 to 50 ppm, this region contains signals from sp3 hybridized carbon atoms, methyl, methylene, and methine groups. 50 to 100 ppm, this region contains sp3 hybridized carbon atoms that are deshielded by electronegative atoms, just as sp hybridized carbon atoms. 100 to 150 ppm. This region contains sp2 hybridized atoms. Okay. 150 to 220 ppm. This region contains the carbon atoms of a carbonyl group. These carbon atoms are highly shielded. So now loose stuff falling. Okay. Predict the number of signals at the location of each signal in the expected CNMR spectrum of a falling compound. Begin by determining the number of expected signal. The compound has 5 carbon atoms, but we must look to see if any of these carbon atoms are interchangeable by symmetry. In this case, there's symmetry, and we expect only 3 signals in the CNMR spectrum. The expected chemical shift shown below are categorized according to the region of spectrum in which signal we expect to appear. Okay. I'm done. I'm done reading this. Oh my god. Oh my god, bro. Woo! Okay. I have a little bit understanding now of NMR and CNMR, which is good. Now all I have to do is basically just practice a lot with assignments and no, not assignments, like practice problems, past exam papers, and then I'm good to go to the exam. Then I'm gonna wreck them all. But yeah, I'm glad I did like um yeah. Uh I'm just checking if I need to read more. If I had more homework for. Hope not. I think I read it all. Especially quantum mechanics. I did read it all with you guys. Hmm. 28th May 1st. Oh shit. Okay, so I have to read about particle in a box. I did that. Tunneling. Okay, I need to read about tunneling and then I'm done. Cool. How long has it been? 3 hours? Holy shit. Okay. That went so fast. Okay. Anyway, let's read this last part and then that's about it, man. Tunneling. It's like Mario. Boom. Give me a moment. I have to check. Oh, what? Uh, um. Alright, how much do I need to read? Okay, that's doable. That's doable. Yeah, we got this. Tunneling, everybody. Tunneling. Tunneling, man. Let's do this. Okay. Do not rise to infinity in a real system meant for partitioners such as the shown. Oh my god, there's these stupid words now. I have to read. Okay. The rectangular partitional energy barrier. Consider a particle incident from the left of the rectangular partitional energy barrier. A one-dimensional barrier of constant height and infinite width. If the energy of the particle E is less than the partitional barrier height V, then according to the classical mechanics, the particle will be reflected off the partitional wall. However, according to quantum theory, when a particle is inside the region representing the barrier, its wave function does not decay according to zero, but rather varies smooth and then on the far side of the barrier oscillates again. The net result is penetration through the classical forbidden region, the phenomenon known as tunneling. The potential energy do not rise abruptly to infinity in real systems. In the arrangement shown here, a particle placed in the well between the potential barriers can penetrate through and into and through the barriers on either side of the well. Topic 9 presents the solution of the Schrodinger equation for a particle confined between two walls and potential energy barriers that rise abruptly to infinity and prevent the particle from being found outside the walls. However, potential barriers um Yeah. The Schrödinger equation is used to calculate the probability of tunneling of a particle of a mass m incident from a left on rectangular potential energy that extends to x equals 0 to x equals L. On the left of the barrier, x is smaller than 0. The wave function of those are those of a particle with v equals 0. So from equation 9.3 we can write this shit. The wave function of the left of a barrier. The Schrödinger equation of the region representing the barrier 0xL, where the potential energy is the constant, V is. We shall consider particles that have E is smaller than V. So according to classical physics, the particle has insufficient energy to pass through the barrier. Therefore, the which V minus E is bigger than 0. The general solution for this equation are okay. As can be verified by differentiating the wave function twice with respect to x. The important feature to note is that two exponential in equation 10.3 are now real functions, as distinct from the complex oscillating functions for a region where v equals 0. To the right of the barrier, x is bigger than L, where v equals 0. Again, the wave functions are of the right barrier, okay? Note that to the right of the barrier, the particle can only be moving to the right, and therefore terms of the form E minus IKX. Do not contribute the wave function in equation 10.4. The complete wave function for a particle incident from the left consists of figure 10.3. A incident wave A E I AEI kx corresponds to positive momentum. A wave reflected from the barrier BE minus IKX corresponds to negative momentum, motion to the left. The exponentially changing amplitudes inside the barrier, equation 10.3. An oscillating wave, equation 10.4, representing the propagation of the particle to the right after tunneling through the barrier successfully. The probability that a particle is traveling towards the positive x to the right on the left of the barrier, x is smaller than 0, is proportional to modulus of A, and the probability that is traveling to the right on the right of the barrier. X is bigger than L and is modulus of A mark. The ratio of these two probabilities, which reflects the probability of a particle tunneling through the barrier, is called the transmission probability T. To determine the relationship of modulus A mark and modulus A, we need to investigate the relationship between the coefficient ABCD and A mark. Since the accepted wave function must be continuous at the edge of the barrier at x01 and xl, remembering that x0 equals 1 is A plus B. Okay. Oh my god. Where E. Oh, no. Where was that? Oops. Where epsilon equals E divided by V. This function is plotted in figure 10.5. The transmission probability E. Should I read it like this, maybe? Nah. T increases as E approaches V, the probability totally increases. T approaches but is still at then 1 for E is bigger than V. There is still a probability for a particle being reflected by a barrier where even when classically it can pass over it. G1 for E is bigger than V expected classically. For high wide barriers in the sense of KL, okay, the transmission probability decreases exponentially with the thickness of the barrier, and with M in half. For the particles of low mass are more able to tunnel through barriers than heavy ones. Tunneling is very important for electron and muons, and moderately important of protons. For heavier particles, it is less important. A number of effects in chemistry. For example, the isotope depends on some reaction rates. Depend on ability of protons to tunnel more readily than the deuteron. Deuteron? What the hell is that? The very rapid equilibration of proton transfer reactions is also a manifestation of the ability of protons to tunnel through barriers and transfer quickly from acid to base. Tunneling of protons between acidic and basic compounds is also an important feature of the mechanism of some enzyme catalyzed reactions. A reaction as a function of a reaction coordinate topic with the reactants on the left of barrier and the protons on the right, the transmission probability for the EC chord barrier can provide insight into the nature of a chemical reaction that proceeds by tunneling through a potential energy barrier, such as those involving the transfer of electrons or protons over short distances. An analytic expression for the transmission probability for an EC chord partitional function can be found by solving the Schrödinger equation, which is in this case is, oh my god, what in the hell is this, man? Oh god. Okay. Okay, the double wheel partitional. The double wheel partitional shown in figure 10.9 provides a useful model for variety processes which can occur to resulting of a tunneling through a barrier. They include electron or proton transfer from a donor to acceptor, electrical conductivity between two nanoparticles, and conformational change of a molecule. Here we can focus on the last of these processes and consider conformational changes in the trigonal pyramidal AB3 molecules such as NH3 which shall represent the potential energy of the conformation AB3 by the left hand wall, and the potential energy of inverted B3A molecule by the right hand wall. The potential energy when the pyramidal molecule has been flattened is represented by the barrier between walls. If the barrier is high, invasion is difficult, as for well-made umbrella. If the barrier is low, invasion by tunneling readily occurs. When the potential barrier is infinitely high, in practice very high, the two conformations AB3 and B3A cannot interconvert. Beat it, beat it, beat it, beat it. Don't remember to beat it. Don't remember. Beat it, beat it. Oh! Ah! Sorry. I'm having slight issues with my throat. Pause. That came out so wrong. Beat it, beat it. Okay, let's get this over with. Into convert, we denote the ground state wave function of AB3 and wave function 1, and that of B3A by pi r. The two wave functions have the same energy. When the barrier is lower, tunneling can occur. We call figure 10.3 and the wave function pi L seeps through the barrier and has non-zero amplitude, where psi R, which also seeps through the barrier, is non-zero. The conformations AB3 and B3A can now interconvert, and we seek a new wave function to describe the composite system. The wave function must be delocalized or both of the potential energy wells of the double well potential. One such unnormalized wave function is the linear combination. Okay, what the hell? The coefficients of psi L and psi R in the linear combination are equal because there are equal probability of finding the molecule in either AB3 or B3A conformation. We call postulate 5. The function wave function L and wave function R can also be used to form another linear combination capable of describing the composite system, namely the unnormalized wave function. So psi R, wave function L minus wave function R. Again, there are equal probability of finding the molecule in either potential well. The wave functions, okay, are this depised in figure. They have different probability amplitudes, especially in the vicinity of proportional barrier. Has a node in the middle of the barrier, and as a result, these two linear combinations have different energies. The state described by the linear combination psi L and psi R is lower in energy. Its actual value depending on the height of a barrier that occurs on tunneling through the finite potential energy barrier has a result in two states, delocalized over both of the potential energy wells and having different energies, a phenomenon known as invasion doubling. Holy shit, that was a lot to read. Checklist of concepts, come on. Penetration, pause, through a classically forbidden region is called tunneling. The probability of tunneling decreases with an increase in the height and width of the potential barrier. Light particles are more able to tunnel through barriers than heavy ones. The EC chord potential is a useful model to describe potential energy barriers in chemical reactions. Tunneling through a finite barrier separating two potential wells result in states delocalized over both wells and having different energies, a phenomenon known as invasion doubling. Cool. Now, ladies and gentlemen, I did all my homework. Bro. All my homework for this week with you guys, so you can see how productive I am. Oh my god, there's a lot to read. There was a lot to read, bro. Oh yeah, I have to show you guys something. I had to show something. Okay. Yeah, I have to show you something. Wait. Give me a moment. I saw something shock. Okay. Interesting. Gonna show you something really shocking. Like, I was like, what the hell did I just read? Like genuinely, I'm never gonna read my YouTube comments again. Like I was like, how you? I was like, how are you? Yeah. Watch what I'm gonna. Absolutely. Let me pull this up. How the hell? Give me a moment. Ladies and gentlemen, give me a moment. I'll be right there. I just need to hide his name because I respect privacy. I respect everyone's privacy and they are allowed to have privacy. There we go. That should be better. Now look at this shit. Let me show you guys what I mean. Like I was how the hell can I show this? Wait. I was like checking my YouTube comments. Alright. I was checking my YouTube comments. Why can I what? There we go. Okay, so basically what happened. Okay. So I was checking my YouTube. I can't even speak anymore after this shit. So basically, I was checking my YouTube comments. I was just curious, checking if I got a comment, and I got a comment. And I wanted to see what the hell this comment was. This is the comment. This is the comment I got. On a freaking chemistry video. Of a freaking benzene ring. A benzene ring. A benzene ring. A benzene ring. I'm saying it again. A benzene ring. And I got this freaking comment. One can only goon to this shit. Brother. How are you so down bad? How are you so down bad that you want to goon to a freaking benzene? Like, what the hell? Nah, Gina, what the hell did I just read? Like, I was minding my own business during the day, and I was like, oh, there's a comment. Let me read that. And then I read it, and then it just said, one can only goon to this shit. What do you want me to do? What do you want me to do? Like, such a random comment, even on a chemistry video, too. Oh my god, I hope not my comments are gonna get that wild. But this is just, yeah, you guys are wild. Stop gooning to freaking benzene rings. My god, stop. Stop it. Stop being weird. Yeah. So yeah, that's basically what I want to show. People apparently gooning to freaking benzene rings. now I'm just wondering what the hell am I supposed to do? Like, I already did all my homework like a good boy, and being productive is honestly the best thing. Just promise me you don't go into freaking benzene rings, man. It's not the most optimal thing. Like, calm down, bro. But yeah, I wanted to show you that. That's basically it. Uh, but yeah, we've been streaming freaking 4 hours, and I did promise you guys that I'm gonna stream a long time. I am a man of my word. Well, what I say is what I do. No, I feel good after streaming 4 hours. Oh yeah, actually I want to show you one more thing before I get the hell out of the way. Let me see here. This is actually incredible. Mm, 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 mm. Un momento. Un momento. I have to. How do I get? Oh well. Let me show you guys this incredible stuff. What the hell do I do to get screen, right? Yeah, screen. This one. Oh, let me show you something that is so surreal. What happened? Look at this. So basically, when you search my name up on Google, on freaking Google, my Twitter account pops up, my Instagram account pops up, my YouTube video too, and then you're wondering, what the hell is this? What the hell is this one? Zanium, the element of no limits. What the hell is this? Let me show you guys what the hell I'm talking about. So when we click on this, oh my, why is it so zoom out? Oh my god, look at this. Look at this. Oh wait, there we go. Should be like this. Okay, let me refresh. Wait. This is some historical shit right here, alright? And I'm so happy. Let me try this. No. Should be more like this, baby. Yeah. So look at this, basically. We have a sweet welcome to Zanium, the element of no limits. That's our element, basically. So as you can see, at the start we have our sweet logo. Oh my god, our sweet community logo. And then we just have to click anywhere, and then we have the periodic table. There's still gonna be changes to the website, don't worry about it. So, and we just tap here. This is just the periodic table to see all the elements. So we just check it. Welcome to Zanium. Oh my, and then we go in. Oh! Welcome to Zanium, a chemistry content creator and streamer driven by one goal: to make science click for everyone, turning confusing into clarity. From I don't get it to this is actually amazing. This is what I'm talking about. This is what Zanium is. So yeah, I have my own website basically. If you want to check it out, it's zanium.net basically. Or just search Zanium now. I'm pretty much famous, Mom, I did it! No. Well, it's pretty much one of my dreams to make a website, and it happened. So yeah, definitely there's gonna be more updates to the website. Don't worry about it, it's not complete yet, but I have a website now where all my stuff is gonna be. And so when you go down, there's my channel growth stats, live stats. There's gonna be a whole category to that. So I have my stats with YouTube or TikTok, everything, all how many videos I have, so just a space for me to see my growth basically. So that's pretty cool. And then instead of this YouTube counter, I can use my own counter, my very own Xenium counter. So we have like this education, community, global, and yeah, I'm acting like I'm trying to go for global community. So yeah, fresh from the lab, my recent video is here if you haven't seen it. The element of no limits. Watch mind-blowing chemical reaction from synthesizing compounds to explosive demonstration that push the boundaries of science. And all that element 119, our element number, atomic number, baby, let's go! The fictional element at the heart of Xenium, representing limitless potential and the spirit of significant discovery. Ooh, that's some good shit, bro. A passionate community of chemistry enthusiasts, students, and science lovers, united by curiosity and discovery. And then we have Ready to Explore, some, like, yeah. So you can join Discord and subscribe me on YouTube there. So that's pretty cool. So the categories, we have videos, we have home, then we have videos. So all my videos are here. Past live streams also. And what the hell is organic chemistry, my playlist. So yeah, it's getting there healthy. And yeah. So we have like visit YouTube channel and watch Xenium. Then we have learn. This is the category where I want to make a learning platform. So basically, like every branch of chemistry, there's gonna be every branch of chemistry here explained easily and just very easily that everyone can access. No like like this what is called like money bullshit that you have to buy some subscription bullshit. Nah, this is available to everyone on earth, and everyone can learn chemistry with no stress and easy explain. Like, what is an atom? An atom is a nucleus, protons, neutrons surrounded by electrons. The number of protons defines what an element is. Visualize a tiny solar system but with quantum rules. So basically it's just like this. This is just like a startup, like a beta version. So there's gonna be more. Yeah, so more concepts are coming soon, written by Xenium. So yeah, it's gonna be more, and all branches of chemistry will be there. So organic, general, analytic, quantum. There's also gonna be quantum, and physical, inorganic. I didn't say inorganic. Yeah, inorganic, and yeah. So it's gonna be good. This is one of my biggest plans. And then we have about me, just a little thing about me, like who am I? So one of my quotes is basically, chemistry was never too hard. It just wasn't explained the right way. That's basically what I mean. And I create content to students who feel lost in class, the curious minds who wants to go deeper, and the people who were told this just isn't for you. So those who didn't, like their teachers said that chemistry isn't for you, just try something else. I want to make sure that everyone can understand it. So yeah, make chemistry accessible, global, and actually enjoyable, turn confusion into clarity, prove that learning science doesn't have to feel like suffering, basically. So yeah, and chemistry, content creation, and yeah, just bigger than content. So join the Z community and be a part of the journey as I grow into a scientist. And yeah, honestly, this is just surreal. And merch, what is this? Merch, Xenium merch collection is being crafted. Premium quality, limited edition pieces representing the element of no limits. This is just a space like when I actually make something someday in the future. I don't know when, but in the distant future, I will want to make a merch, like my own like merch, Xenium merch. And yeah, I have some ideas in mind, but we'll get there. This is just a like concept, so nothing serious now, but it's just there. So it's a little thriller, like a thriller movie. And then we have my social media, everything: YouTube, Discord, Twitter, TikTok, and also need to implement Instagram too. And yeah, latest from YouTube. And yeah, so nothing of this could be accomplished by my developer, Joxy. So as you can see, it's powered by Joxy service. Okay, no. So yeah, powered by Joxy services. Basically, he is my developer, and yeah, I appreciate him so much. But yeah, I really appreciate you, developer. If you're seeing this stream, I don't know if it's even seen this stream, but I appreciate you so much. Thank you so much. Thank you so much. Thank you so much for making this possible. With your teamwork and your like presence, and just like, I really appreciate you, man. And thank you. I hope we're gonna grow bigger and stronger every day. And yeah, it's honestly incredible. But yeah, I have a website now, and yeah, check it out, Xanium.net. You can just check it out on Google. You just type Xanium, and then I'm gonna pop up everywhere like a pop-up ad. Yeah. So, what else do I want to explain? There's not much anymore though. I've been streaming for like 4 hours now, so I guess this is a very good time to end. 4 hours and one chatter. Let's go, baby. Let's go. Yeah, I really don't have any more things to add on. Just want to say thank you for watching this stream. Yeah, I appreciate you guys so much. Thank you so much for the support. We're almost at freaking 60 subscribers, which is surreal. Like, I think after like what, yesterday or 1 week ago we hit 50. That's like a lot of people. That's like 10 plus people adding up to our community. And I appreciate my Xanium community, my Z community so much. And yeah, we have no limits, baby. We're gonna get there. And hopefully you're gonna stay productive and do your studies and all that shit, bro. Gonna make it. Gonna make it. Don't give up. Don't ever give up. There's always a way. So yeah, I'll see you next stream. It was fun. It was pretty fun to, well, definitely fun for me to complete my homework. Like all my homework I needed to this week, so I'm basically free now. Yeah. Tomorrow is gonna be lab exercises. Am I gonna stream in the lab? I don't know. If I'm lucky, then I'm gonna stream in the lab. But for now, I'll see you next stream. And new video is coming out soon. Don't worry. So yeah.